So I'm going to set the scene. So for those of you not familiar with the Grantham Institute, we are in the college what's known as a global institute. So we are meant to be basically a shop window to the rest of the world about all the aspects of climate change and environment. The core research is done in departments all across the college, but we are sort of one access point for external interests, for example. So what I was just going to try and do is maybe set the scene around climate change. So much of what I'm saying maybe is familiar, some of it may not be. So the observational evidence has obviously been accumulating. So here's a diagram a graphic that shows what's been happening in a very pictorial way. So the circle represents the annual cycle and the different years you can see. And you can see sort of this emerging redness, which of course is the warming. And now we're in, if you look at the bottom column, I mean, the warming is just continuous, persistent every month. It is relentless. So one of the things we always get asked, so a lot of media attention, well, is this affected to climate change? What can we say about the variables? So I think it's actually quite useful to have sort of rules of thumb, because you can go to climate model projections, which of course are very important for any aspects of adaptation and so forth, but you can also get a little bit too involved in the details. So it's good to sort of have some rules of the thumb, which are basically based on physics. So those are sort of communication tools as well to non-experts, and that we can be reasonably confident about statements. So we believe that the rules of climate change is that it will get hotter everywhere, because CO2 is a long-lived gas. We're talking about a long-term change, so not 1 year or the next. We're talking about multi-year. When I talk about climate, some people take 30-year averages. So on that basis, it will be hotter everywhere. So that's sort of one rule of thumb. These are all rules of thumbs, of course. The other fact we know is that when the atmosphere is warmer, it holds more moisture. More moisture means it's going to be wetter on average when it does rain, and more rain just can give you more floods. So the details, of course, how much more floods and how many more meters, that's of course all up for debate. But the direction is warmer, moister, wetter, more flood is reasonably consistent. The third one is sort of less well known, but I think also quite important, a little bit more debatable. So the wet regions get wetter and the dry regions get drier. There's good physical reasons for that as well, but I won't elaborate on that. So that tells you a little bit more locally about your geography, what you might expect. I think the fourth one is what I'm going to elaborate on a little bit further, because I think that's a really, really important point, which I think has a direct impact to what you talk about for the rest of the day. And that's what I call the uncommon becomes common. And so what do I mean by that? So here's an example of a climate variable. It could be almost any variable. I just picked the most simplest one, and that sort of looks like a Gaussian normal distribution in most places. So it's the simplest climate variable we can think of. And so there are two curves here which are overlain. You've got the thinner curve. I've got a pointer, so I'll use my hands. So you've got the thinner curve here, which is sort of the current climate. So you've got an average state, and it's slightly colder, slightly hotter. And this the point about this distribution is it's not meant to be the seasonal cycle. It's meant to be corrected for the seasonal cycle. So this is actually says this could be the average January. This could be the average July. It doesn't matter. It's a little bit a little bit colder or a little bit hotter. Okay, so then you have climate change, and so the mean shifts. And that's here. So that's what we see most of the time. So if you imagine then people arguing about global warming of 1 degree, 2 degrees maybe, unfortunately, or even higher. If you think about it as an average temperature, that's not that problematic in the sense that what I would call it's an adaptive zone. So this is what we mostly expect, right? So even day to day, we're used to 1 degree warmer, colder here, there, everywhere. We just change our clothes, we close the window, we turn on the heating. We sort of adapted to fluctuations around the mean. We know what happens in January, we know what happens in July, we're reasonably prepared. But then you get over to the utter end, so let's get the hotter bit. So then you're getting into the first bit here. So you in the past, you have said, oh, this is quite hot. So that might have happened, I don't know, every 10 years or 20 years. You think, it's really quite hot. And then suddenly that seems to be happening every 3 years. Okay. I'm beginning to sense it, right? So this is our our intuition or the narrative when you start hearing, oh yeah, it does feel different, if I can still remember going back, if you're old enough, then, but it's still not necessarily critical. It's just a perception, because it's in your own experience, your own assessment of probability of risk. You sort of get a sense of, oh, this is a little bit more than it should be. This, of course, then is the problem. This is where things start breaking. This is where people start dying. This is where real damage happens. Now, we're all adapted to this area, and we try to mitigate these very low probability, high impact events. And then when you have a problem with the probability distribution shifting, you end up in this regime which I call the unseen. So suddenly there are things which are just out of your experience. They're out of all of the data records, but they are just a natural consequence of this probability distribution having shifted. And we don't really have any understanding about this. So we don't have any observations about this. The climate models also don't really deal very well with this as well, because it's really at the extreme end. They sort of deal with this bit here. Climate models really struggle to deal with these 1 in 100 year, 1% probability events. So it's an unseen environment. And so what the IPCC, so this is the Intergovernmental Panel on Climate Change, has been, they've been sort of producing these types of maps and assessments. So increasingly, they're quite confident that human-caused climate change is already affecting weather and climate extremes in every region. This has led to widespread adverse impacts and related losses and damages of nature and people. High confidence. So as the IPCC has evolved, you see there's a 6 there. So this is a 6th iteration. It goes every 5 years. So it's been going a long time. The statements are getting more and more aggressive. I remember the first statements, and they really didn't want to say anything about extreme weather. This wasn't there. They just, the global mean temperature, we think it's going up. So they're coming increasingly more related to that. And similar to what Neil was saying, there also is a narrative which is moving away from the weather. It's more and more about impact, because impact then is what it's about. I mean, I love the weather and studying the weather, but at the end of the day, it's about the impact. So people are beginning to attribute things like water availability and food production, saying, well, can we detect changes? And you can see that they do going rather elaborate, if you like, system where you say you've got adverse impact, you've got adverse positive impacts, not many of those. Climate change driven observed, but no global assessment made. So these are the grays, we're not really completely sure. Then they have this idea of confidence, high confidence, medium confidence, and low confidence. That's the different stars. So you can see that there's all sorts of different sectors. I might go through them. But the evidence is sort of mixed. So some places it's quite clear, some places it's immature. The history of this, though, is that it all starts with 1 star and it seems to end up with 3 star. If you wait long enough, the 3 stars just seem to appear if you've seen enough IPCC reports. So that's sort of where we go. And they're also then, now they're getting to even more complicated, talk about multiple physical climate conditions, which are increasingly attributed to human influence. So drought, for example, isn't just about rain. It's also about the soil content. It's about the temperature and the rain. So there's lots of variables you sort of have to understand to get to those points. So then they've identified all sorts of additional factors. So the variable that's the most well understood is the hot extreme. So here is an assessment where they try to assess, well, how much of the change in temperature can we really be confident is due to climate change? And you can see here, so again, you've got this confidence, the dots, 3 dots is high. And when has there been a change in the extreme? So the red means there's been a change, the blue means a decrease, and shade means limited data. And you see that temperature, which is quite well-behaved variable and well-measured for a long time, the signal is clear. Wherever you look, there are more hot extremes. And it's in certain places, like there, you're almost certainly limited by data. Interestingly, though, of course, this is quite an important part of the world. They seem less convinced, but like I said, with time, things move on. So that's the temperature. And like I said, that was sort of my first rule of thumb. So that's where that comes from. My rule of thumb was about rain as well. And there you can see the pictures are a lot more mixed. So here again, human influence, particularly greenhouse gas emission, is likely the main driver. So likely, so that's a lower, much lower bar. You can put a percentage on it if you want, but it's definitely lower than temperature. And then you can see that here is an increase in 19 of the areas. Low agreement is 8. Limited data and or literature 18. So almost as big as the increase, right? And then you suddenly have these big holes over Africa, Latin America, and large parts of the world. So just to be clear, that doesn't mean there isn't a change. There almost certainly is, actually. It's just if you want to make a scientific case, which is the IPCC need to do, you need to pass statistical significance. To pass statistical significance, you need a sound, long record. If you haven't got that, if you've got a very noisy data, very noisy model, you need a lot of observations to get the signal. So it doesn't mean there isn't a signal. It means they can't detect it in many places. So that's another thing to bear in mind. Very often, changes are happening. We can't just detect them. And I think we're increasingly confident that things are changing, even when we can't detect it just yet. But particularly for rain, the global trends are not the same as the local trends. So there's definitely, because of the way the variability manifests itself, there's definitely regional patches which emerge much earlier because you've got better data, or maybe the baseline is much more stable, so it's much easier to detect a trend. So I think this is quite a powerful figure, maybe one of the most powerful figures from the IPCC. So it borrows the color scale, which I started off with the circles, but it does it as a bar. So you've got a bar chart here, which is the global temperature. So the blue is anomalous to 1850 to 1900. Sounds weird. It's what we call the pre-industrial period. So before there was substantial greenhouse gas emissions. So we take that as a baseline. So you've got this sort of going from blue to orange, going to red. So that's more or less the same thing as I described to you. And here they have an interesting perspective where they just draw people's when they were born. And so what they would have expected. So if you were born in 1950, you would have maybe sensed that things are warmer. Certainly in 1918, you would have sensed it. And the generation now, well, what are they looking forward to? And I think this is another important point, which some people, I'm sure everybody in the audience grasp, but I think I'm afraid some people don't completely grasp. So you've got different emission scenarios here, right? So this is a very high emission scenario. Some people would argue it's almost implausible, but if you have Donald Trump in every country in the world, this is plausible. You've got high, you've got intermediate, low, and very low. So very low would be very aggressive. So these two are probably outliers. But actually, if you look at it, no matter what we do, you are in red, right? So this is not like air pollution. You stop the emissions and you can sort of try and get back to normal. We're not going back to normal. We are committed. We are committed to red. We are red, deep red, if you're not careful. But red it's going to be. And going back to my other diagram about the unseen, we are only just beginning to enter this red zone, right? So actually, in terms of what that means in terms of extremes, we have absolutely no idea because all of our data is this. So there's a little bit of warming. So if you were wondering to know, well, what is an extreme event? It might be 1 in 50-year event or something that's really catastrophic. You've got no idea. And in fact, we have no idea. But what we do know is that we are committed to it. We are committed to this level of warming for the current generation, for many generations to come. And we have very little understanding of what that means. Now, the assessment of risk has also changed with time. So here's a chart which sort of tries to identify different things. So is there health? There isn't a health one here, but maybe unique and threatened systems. So there was an understanding that in the AR5 that the threshold for that being material was maybe at 1.2, but now there's evidence that it's already happening, and you can take all sorts of variables and you end up with the same sort of conclusion. So that not only has the global warming increased, people's understanding of what actually that means in terms of risk has increased, so that we are also understanding that the level of danger is much closer than it was. And what are we doing? Well, not very much. I mean, this is the implemented policy, so COP is coming up. So we're sort of arguing about this, really, what's happening. And you can see here that this is sort of what people claim that the target is, and the red is the implemented policy. So this is the gap, as they say, and the gap is huge and it's growing, and it doesn't look like it's going to be closed anytime soon. And we won't go into the politics of what's actually happening in the rest of the world. going to talk about the probability. So another way of dealing with this problem is the carbon budget. So how much carbon have you got left? And this is a picture that tries to show that if you want to achieve a certain amount of warming, then you have a certain amount of carbon that you can emit. Because carbon is in the atmosphere for thousands of years, you have a budget. Every molecule of CO2 you put in the atmosphere adds. You're just filling the tap. You're not draining the tap by stopping the emission. You're just filling the bathwater. So that's your budget, and you've got various targets, and we are not within reaching them at all. Of course, on a positive note, what we need is lots of change across all the sectors. So that's the first statement. There needs to be upscaling of the mitigation and adaptation options, including what we'll hear about today. So it needs to be more than field trials. It needs to be all the way up to on continental scale, all encompassing. And there's high confidence that actually the solutions are here. And I think you'll hear about some of the solutions today. And that's it.